By the end of this lesson, you should be able to describe situations where forces are in equilibrium. State what is a resultant force. Add two forces to determine the resultant force. Solve problems involving situations where forces are in equilibrium. Observe these various situations. What do you understand by the term state of equilibrium? Analyzing forces in equilibrium is a major part of a design engineer's work. Knowing all the forces acting on a particular structure helps to determine the stability of the structure. An object is said to be in a state of equilibrium when the object is at rest, moving with uniform velocity. A book at rest on the tabletop is in a state of equilibrium. There is no unbalanced force acting on the book. What does no unbalanced force acting on the book mean? There are two forces acting on the book, the weight of the book and the normal reaction of the tabletop. The weight of the book is balanced by the normal reaction of the tabletop. There is no unbalanced force acting on the book. An object is said to be in a state of equilibrium when there is no unbalanced force acting on the object. An air puck moving with uniform velocity is also in a state of equilibrium. The forces acting on the air puck are the weight of the air puck and the normal reaction of the table. As the track is smooth, there is no frictional force acting against the motion of the air puck. There is no unbalanced force acting on the air puck. The weight of the air puck is balanced by the normal reaction of the table. An object is said to be in a state of equilibrium when there is no unbalanced force acting on the object. The picture frame hanging on the wall is said to be in the state of equilibrium. Why? If the picture frame is in equilibrium, then the net force acting on it should be zero. Let's look at the forces acting on this picture frame. The tensions of the string that hangs the picture are T1 and T2. The string is at an angle theta from the picture frame, and the weight of the frame is W. With the length of an arrow representing the magnitude of a force and the direction of an arrow representing the direction of a force, the resultant of the forces acting on an object can be obtained. When the three scaled arrows representing the forces T1, T2, and W are drawn from end to end, they form a closed triangle. Therefore, the forces T1, T2, and W are said to be in equilibrium. The vector addition of these three forces will be a net force of 0 Newton. Another way of determining the net force acting on the picture frame involves the resolution of forces into components that are perpendicular to each other. T1 is resolved into its components T1 sine theta and T1 cosine theta that are perpendicular to each other. Similarly, T2 is resolved into T2 sine theta and T2 cosine theta. The resultant of the vertical components must be 0 also. T1 sine theta plus T2 sine theta equals W. The picture frame is hung this way with the tension of strings T1 and T2 making an angle theta with the frame. Since it does not move, it is in a state of equilibrium. The net force acting on it should be 0. Horizontal force, T1 cosine theta, equals T2 cosine theta, and vertical force, T1 sine theta plus T2 sine theta equals W. Ahmad and Zaki are pulling a boat along the river. Each of them exerts a force of 600 newtons directed at a 30-degree angle relative to the forward motion of the boat. The boat moves with a constant velocity. What is the resultant force acting on the boat? By completing the parallelogram, the resultant force is represented by the diagonal of the parallelogram. As a result, the boat moves forward in the direction of the resultant force.
Let's carry out an activity to study whether the system is in equilibrium. Click on the slider bar to increase or decrease the number of coins in the bucket and also to balance the mass of the metal ball. Click on the Start button to observe what happens. When the total mass of the bucket and the coins is the same as the mass of the metal ball, are the forces acting on the system in equilibrium? Draw a diagram to explain the forces in the system for each situation where the total mass of the bucket and the coins is the same as the mass of the metal ball. The total mass of the bucket and the coins is less than the mass of the metal ball. The total mass of the bucket and the coins is more than the mass of the metal ball.